Hello everyone, this is Vasu Bhardwaj from Michigan Tech. In this particular presentation, I'm going to walk you through how I performed voice code characterization on my low friction test bed wave energy converter. So this is the complete instrumentation setup which I've used on my wave energy converter, in which the voice coil is the most critical thing. Voice coil use an actuator and generator to make that low friction test bed work and execute controls or generate electricity out of it. So one of these steps involve characterizing this voice coil and how and why it's important. I'm going to walk you through. So now moving to next slide. Okay. Yeah. So so we were using HTW voice coil, and it have stroke length of 85 mm. It produces 38.7 Newton of force, of peak force at 2.6 amp input, and it produce 116 Newton of force at 7.8 amp input, which have 10% duty cycle. So like these are the only information which we have of our voice coil by HTW, but to execute controls or using that voice coil to command some specific force, we need to characterize it at each and every position information, and we need to get some graph like that. So when this voice coil move inside, we have a force curve which look like this. So we need to have a graph something like this, and that's the reason we perform the voice coil characterization. And moving forward, uh, I'll just give you how the things look at the end, and then I'll walk you through like the scripts, how those lookup tables were generated. So if you talk about the setup of how the characterization was performed, we get the vac out from the web tank, and we form a sort of a zig where the complete back end of the vac is fixed to a frame, and then we were moving the connecting rod, which is connected to the voice coil, at different positions, and we commanded some current input and measure the force output for that current input. So we divided the whole stroke length of 85 mm in 16 points, which consist of these 5 mm shims, and we moved at different position, commanded a sine wave current input to have the current data. So using that current data at different position, we were able to evaluate that particular uh, plot, which looked like that, which consists of force constant, which is Newton per amp, and at all across the position data. And further, we can use that particular model to inverse it to calculate current for different force values, and that's pretty useful. Um, and after doing the characterization, we did some validation part, which consists of up here, like you can see how the the blue line is the commanded force and the orange line is the measured force. So we commanded around 7 Newton of force, and when the moment current goes at different position, we moved it, and we can see a constant current. These peaks comes up because like I was removing these slits, and like we can see the transition, but overall it come up with a constant force whatever we commanded. Similar thing was performed on a sine wave. So up here we commanded a 4 sine wave in blue, and then the orange is the actuation force calculated by, like, measured by the load cell, and the commanded force and actuation force always almost overlap each other, and you can see the error values, which ranges from minus 0.3 to 0.3 Newton. So this shows that our voice coil characterization was pretty good. And further, we also use that particular model for use that as inverse voice coil model, where we commanded some current value, where we commanded some force value, and for that we get the current value, and we probably use that particular model in the controls part of it. That lookup table goes up here, and in that lookup table we give the position data and we get the current constant value, and we from this particular end we come up with the total force command, and then we divide it to get the current output, and that's what we use in our controls model. Now let me jump to the script and show you around how those script look like. So now coming to the script part, in the main script we have two scripts which we need to look at: the load test data and the post process LT. So post process LT is the main script which basically use the load test data script to load data into the main script. Now if we run it, it's gonna start at line 20. It's gonna run that particular script. So if I just go directly into that script and run it, what you're gonna see is we are loading data, and we are dividing that particular we are dividing the data into multiple ranges, and those ranges basically symbols how i- that range basically divide the whole data, taking at multiple position to segregate the data which we are not using, like when the start button is pressed off. So to give you better understanding, first of all, that's how the data look like. That's the force data, um, which is measured, and that's the current data commanded. Current data ranges from -1 to 1 amp in a sine wave form, and you can see that the position data is supposed to be fixed, but it is moving slightly in like 0.2 mm. Which is very less, but like that deformation is supposed to be very less. And that data, if is divided into 16 steps. So if I just type 1 up here and like run section, you will see the very same plot, but this time it would be at 9.4 mm. So our first point was 9.4 mm, where we did that test. And then if we go to, let's say, 10th point, and if I click run section, very similar thing for the, yep. So the 10th point is at around 55 mm, and we have similarly current and force data. And similarly, we have like 16 points in the whole stroke length, which consist of that particular information. And to get you some more understanding, what about I show you how that complete data look like? Okay, wait a second. I was trying it, so I just want to run it directly instead of. Okay. What about I? So if we click on, if we go here and you plot the data, which is the consist. Okay, wait a second. And if I press this, so that's the information, like how many times we press the on and off button. So it would be like 16 times we perform that, and each time we commanded some current. So if I do that, and if I press hold on, and then I the same thing. uh, So now you will see a plot. So that's how actually we perform that test, where we have like multiple points. And so these are the same current input given at the 16 different points. So that's why like, I just want to show you like how the real raw data look like. And then we divide the data into multiple points, and then we have something like that, like segregated, like each and every position data is divided into different ranges using like for loop, and then we use that particular data. Now coming to the main script, using that particular data, uh, we we calculated the coefficient, or like force coefficient of the different position. So for that, the drill was, we take the current and force data which have a linear relation between each other at different position, and find its slope value up here. For that we use polyfit. So if I just show you how the current and force relation look like at different point, uh, and so what about I come up with a plot. So that's if I use, wait a second. So if I use that particular plot, it consists of, so run to the end. And now if I just come up with, yeah, so when you run that script, basically you see all the lookup table which we're supposed to make, and that's the one of the uh, important lookup table, which consists of slope information at different point, and that's what we use in our main script to use inverse voice coil model or executing controls. And to make the slope at each and every position, we did what we basically use the polyfit command to find the slope between the current and force, like the current commanded and and the actuation force measured on the load cell, and using the polyfit we were able to calculate the slope between both the two. Another approach, you can also divide both the thing to get the slope. I did with the both way, but I'm using like using the polyfit, like the output from the polyfit. I'm referring that, and so to give you a good understanding of what exactly relationship look like between both of them. So yeah, so that's what you can see. So that's the current input, and that's the force, and that's a kind of a linear relation at the first point, and very similar to the second point. If you press hold on, and then you change it to And so yeah, so it will keep moving like that, and you will have a different slope value for current input to different positions. And that's why we get like, let me show you one more time. And this time I'm going to put maybe 5. So it's a different position. It's probably somewhere 60, like it would be around 40 mm, I would say, stroke length. And you can see how the how this is like, you will get a complete curve where you have slope changing, and the peak slope would be around 14. And then you will get a curve something like you'll get a curve something like this. And then you will use this particular information in a form of a lookup table into a main script. So yeah, that's the general overview. I hope this will help you to perform the like voice call characterization at your end. Yeah, thank you. Goodbye.